The rise of affordable panoramic cameras and head-mounted displays has made 360 degrees images a staple of modern social media platforms like Facebook and YouTube. These high-resolution, immersive visuals offer users a new way to experience content, whether it's a concert, a travel vlog, or a virtual tour of a museum. But with that immersive experience comes a steep cost, massive file sizes that demand significant storage and bandwidth. To manage this, 360 degrees image compression has become essential. Yet the standard approach, projecting the spherical image onto a flat 2D plane using equirectangular projection, introduces two fundamental problems: oversampling and distortion. Let's unpack why. On a sphere, the circumference at the equator is much larger than at the poles. But when you project the entire sphere onto a 2D rectangle, every latitude gets stretched to the same horizontal length. This means polar regions are severely oversampled, filled with redundant pixels that don't exist in the original scene. At the same time, geometry breaks down. Straight lines become curved, shapes warp, and spatial relationships get distorted. These artifacts aren't just visual nuisances, they hurt compression efficiency. The extra pixels increase bit consumption, and the distorted geometry makes it harder for compression models to reconstruct the image accurately. Even recent learning-based neural codecs, which have dramatically improved 2D image compression, still rely on this flawed pipeline. They compress the projected 2D image, but the projection itself remains the bottleneck. So while the models get smarter, they're still fighting against a broken foundation. That's where our work comes in. We propose the first viewport-based neural 360 degrees image compression pipeline, a paradigm shift that replaces image projection with viewport extraction. Instead of mapping the entire sphere to one flat image, we extract multiple small, rectangular viewports, each covering a localized patch of the sphere. Since these patches are small, they can be approximated as flat planes with minimal distortion. The result? Significantly reduced oversampling and geometric distortion. And because each viewport captures only the content it needs, fewer pixels mean lower bit consumption. But here's the catch: viewports don't cover the sphere perfectly. They overlap. And if we compress each viewport independently, like traditional codecs do, we lose the ability to exploit global redundancy. The same person, object, or texture might appear in multiple viewports, but without sharing information across them, we end up compressing the same content multiple times. This is the core challenge: global information loss. To solve it, we introduce the ViewPort ConText, VPCT, module, a transformer-based neural codec designed specifically for this pipeline. VPCT integrates global prior information into the entropy model, the part of the compression system responsible for predicting how many bits to assign to each pixel. VPCT has two key components: an intra-view block and an inter-view block. The intra-view block uses a masked self-attention mechanism to capture causal context within a single viewport. Unlike standard attention, which considers all positions equally, this version only looks at previously quantized pixels, just like how a human would predict the next pixel in a scanline. This ensures the model respects the natural flow of image data, improving prediction accuracy. The inter-view block, however, is where the real innovation lies. It uses a novel cross-view attention layer to model correlations between viewports. When compressing the second viewport, the model can reference the first. When compressing the third, it can use both the first and second. This allows the system to detect and remove overlapping content, eliminating redundancy and boosting compression efficiency. And because VPCT is designed as a plug-in module, it seamlessly integrates with any existing learning-based 2D image codec, be it factorized, hyperprior, joint, or reference. No need to rebuild the entire compression pipeline. Just add VPCT, and you get performance gains across the board. We tested our pipeline on 4 major datasets: LIC 360, Flickr 360, CVIQ, and SaliencyVR, ranging from 1K to 8K resolution. The results were clear. Our method outperforms all prior state-of-the-art approaches, achieving an average of 14.01% bit savings without sacrificing visual quality. Even more impressive, when we integrated VPCT with canonical 2D codecs, we saw consistent gains. The improvement wasn't just in one model, it was across the board. And the gains grew over time. Later compressed viewports benefited more because they could leverage information from earlier ones. Visualizations confirm this. In one example, a person wearing blue pants appears in the top viewport. Their leg extends into the middle viewport. With VPCT, the model recognizes this continuity and uses it to improve compression. The reconstructed image is sharper, and fewer bits are needed. We also analyze the latent space, the compressed representation of the image. The redundancy maps show that with VPCT, the model makes more accurate predictions, especially in overlapping regions. Viewport 1 sees little change, no prior information to use. But viewports 2, 3, and 4 see reductions of 7%, 10.7%, and 15.1% in bitrate, respectively, leading to an average 8.21% savings. But what about cost? We measured flops, memory usage, and latency. Adding VPCT increases computational complexity by only 2–3%, a small price for 11% improvement in compression. And memory usage drops by up to 44% during decoding, because we're processing smaller viewports instead of one massive equirectangular image. We also explored alternatives, concatenating viewports using other transformer models, but VPCT consistently outperformed them. Why? Because it's designed not just to model content, but to understand the 360 degrees context. There are limitations, of course. Performance depends on viewport field of view. Extremely small or large viewports reduce the benefit of cross-viewport modeling. And due to the sequential encoding order, the first viewport can't benefit from others, leading to uneven bit allocation. Future work should explore adaptive faux-V strategies and bidirectional or hierarchical prediction structures to distribute savings more evenly. In conclusion, this paper presents a fundamental rethinking of 360 degrees image compression. By replacing projection with viewport extraction and introducing VPCT to recover global context, we've built a pipeline that's not only more efficient, but also more scalable and compatible with existing 2D codecs. This is the future of immersive media compression. Smarter, leaner, and built from the ground up to understand the full sphere, not just its flat shadow. Our code is available at github.com/jingwalayo/VPCT, and we invite researchers and engineers to build on this foundation. Because if we want to truly live in a world of 360 degrees experiences, we need a compression system that's just as immersive as the content it carries.